All right, for this next session, 3.2 that we have, the derivative as a function. So in the previous sections, we went ahead and discovered that the slope of the tangent line to the graph of f at a point x equals a is given by a limit of secant line slopes. So this difference quotient, this is really just the slope of a secant line. And then we are then moving that secondary point closer and closer to a, which will make our secant lines approach the tangent line at x equals a. Effectively, what we were talking about in the last section was the derivative, but we were not using the word derivative yet. So let's compare these two definitions. The only difference here, effectively, is that instead of a specific, we can think of a fixed point x equals a or a static point x equals a. We now are thinking about, what if we just let this be x? Let's let it be a variable. In other words, we don't want to know just the slope of the tangent line at a specific location x equals a, but what if we want to know the slope of the tangent line at any arbitrary point on the graph? In that case, we would not substitute in a specific value of x, we would just leave x free to vary. And then we'll go ahead and create a new function from f. So this right here, f prime, let's go ahead and just write that in here so we can see that we'd read this as f prime. F prime is the derivative of f. So we start with a function f, and then we can do a process of differentiation. We can differentiate, and we will arrive at f prime, the derivative of f. So this process of differentiation is this process right here. It's the process of forming the difference quotient and then taking the limit of that difference quotient. Okay. So, example 1. Below are two graphs. Sketch all horizontal tangents and then use this information to help you create a rough sketch of the derivative of each graph. So let's remember that what a derivative is. From this definition up here, we see the derivative of f is really just the slope of the tangent line at that point. So for instance, the horizontal tangent lines appear to be here. There's a horizontal tangent. And here's a horizontal tangent. So at this point, I guess x equals 1, the derivative would be 0 because the slope of this line is 0. Whereas over here at 1.75, let's say, the tangent line is this. So the slope must be some positive number, since it's a positive slope. And in the middle here, let's say at x equals 0, the slope of the tangent line, the tangent line, I should say, is that. So the slope it's going downhill, so it should be a negative number. So we use our horizontal tangent lines. That tells us where the slope has to be 0, and then we know that anywhere else besides these locations of horizontal tangents, we know that it then has to be either a positive slope or a negative slope. Some graphs, the derivative might not exist, in which case it's not enough to just know where the derivative is 0. In other words, where are our horizontal tangents? We also want to know if we have any sort of cusps or corners or jagged sharp edges where the derivative doesn't actually exist. But for these two graphs, the function's differentiable everywhere. There's no corners or cusps or sharp immediate transitions. So we're only going to look for, first, where we have horizontal tangents. This tells us the slope of the tangent line at this location must be 0. So then over here, we're going uphill. So we have positive slope tangent lines. And then as we get closer to this peak here, the tangent lines are getting less steep. And then they get flat, and then they start getting steeper in the negative direction, less steep, flatten out, and then more steep and positive. So we can see a transition from positive 0 to negative 0 to positive. So what we can do here is when we sketch the derivative, which I will go ahead and do in, I'll do this in black. I'm going to go ahead and draw, I'm going to take my locations, my x values, where we have horizontal tangents, and then I'm just going to mark that location. Because if the slope is 0, that means the graph of the derivative has to cross the x-axis, because this is, well, this is a value of 0. So a slope of 0 means it has to cross the x-axis there. Similarly, this has to cross the x-axis here. So that means the function f and its derivative in black would actually, coincidentally so in this case, intersect one another. So now we can kind of think about sectioning this off. Now look, this sort of divides everything into 3 regions. Over here we have positive, here we have negative, over here we again have positive slope. So that means the function has to be positive on this half, negative in this half, and then again positive. So there's lots of things we can do, we can draw that will have that shape. But if we do so in a nice sort of not too crazy way, what we can find here is that the graph should do something like this. Intersects. And then it has to go back up here, so it has to turn around at some point. And there we go. So this would be the graph of f prime. And does this check out? Yeah. The function, the derivative, is positive here. It means it's above the x-axis. And that checks out because on the left of this dotted line, we have positively sloped tangent lines. 0 at the top, and then between these 2 dotted lines, we have a negative slope. We're going downhill, so we should have the graph being below the x-axis. And then again, we're now going uphill, so our graph should be above the x-axis since we have positive slopes. Over here, again, let's mark the locations of all horizontal tangents. So right there is a horizontal tangent. So we know that the graph of the derivative has to intersect right there. And now if we watch what happens here, this derivative is this graph is symmetric. So that means the slope of the tangent line here is equal and opposite to the slope of the tangent line here. Same tilt, but this is a negative slope, this has a positive slope. So maybe the slope here is negative 12, then this slope here would be positive 12. So because of that, because of the symmetry, we know that our derivative is going to be symmetric as well. So we know that's going to have that property. So if we think about this, the slope just steadily increases as we move left to right. So let's actually go ahead and draw something that's positive. So maybe something like a line. And then here, equal and opposite, so let's just continue. And that does check out. Now, one thing that you may be wondering, and it's natural to wonder, is how did we know to draw, for instance, this in this way? We understand that it has to be below the axis here and above the axis here. Couldn't we have done something like that? Wouldn't that have satisfied? Yes, it would have satisfied it. At this point in the class, you don't really have a ton of information to really know all of the features of a graph. We have a whole section dedicated to this. But for now, it's enough to notice that if a function's increasing, it's going uphill, then we should have positive, be above the axis, Going downhill should be below the axis, and going uphill should be above the axis. If your sketch of a derivative isn't what I have perfectly, that's fine. That's fine. For now, we will learn how to identify those more subtle features to really prove to us it is a line.